Hi, this is NullTeamException with Samuel Marple as our team leader. I'm Kent Sanders, and also on our team is Robert Rocio. So we're going to start our code execution now for task 1 and task 3 so that we can have those executing as we discuss. And Robert will uh, go over task 1.
Yeah, thanks, Sam. So I'm gonna go over task one. I'm gonna do a kind of a talk about what the purpose of the task is, and then do a quick code walkthrough. So the general idea is to test the performance of FNN neural networks at detecting new kinds of attacks for which they were not specifically trained. In order to accomplish this task, we have inside Anaconda and Spider, we've set up an FNN model that's going to kind of test this and demonstrate it. You can see in the code here, we're going to be using the NSL KDD data set, which is divided into 4 general attack classes as well as the normal traffic set. So these classes, as well as the subclasses, you can see are put here into these lists. We read through from the data set, and we then, in the next blocks of code, we subdivide these based upon the attack class, as well as normal traffic. And then we run 6 separate experiments. Each of these is going to try and test how well the model predicts novel attacks based on which attack class it's trained on. So you can see here, we continue to subdivide into training and testing sets based on the parameter inputs to the function. Go down a little bit more, okay? And then down here, we take the text columns out of the data set and encode those as integer values so that they can go into the model for training. And there use a standard scaler. So then we build the FNN. You can see we're using a sequential classifier, and then the rest of the code here is just training and then testing the model. And last but not least, we generate the confusion matrix, which should give us a pretty good idea of the performance of each of these experiments that we've performed with the FNN. So now that I've finished with the code walkthrough, I'm going to pass it over to Sam Marple, who's going to talk about some of our results and findings for this task.
Awesome, thank you. So over there in the right-hand corner, you can see the plots that have been generated during the execution. They essentially show that the model gets better as it gets more training. It makes sense. So we've got results that are popping up here in the window, but we've got a complete set of all 6 experiment results over here in this text file. And they show in the confusion matrix, at first it seems bad because there's a row of zeros in each one, but we trained with normal in the training set. So the testing set consists of solely 2 attack subsets. So it's either it's a true positive or a false negative. Here, the results, as you can see, they're not great, but that is because they were being tested on things that they were never trained on. The best result that we got was almost 40% from training on A1 and A4, testing on A2 and 3. We think that we got the best results there because A1 and A4 are very different, and A1 and A2 are very similar. So having similar things in the testing set where probe may be similar to DOS traffic, and A1 and A4 are very different. So having a varied training set trains you on a wider variety of things and allows the algorithm to prepare for a wider variety of attacks to be tested on. I'm going to pass it over to Kent to talk about task 3 now.
Okay, so task 3. So the code So at the beginning, we set the dimensions for our self-organizing map. So we did 10 by 10 for a total of 100 nodes. And we set our threshold to about 1/2, just because that, after testing several times, tends to give. So here we read in our data set. We scale it so that the numbers are standardized. Our training data is used in part 2 and part 3. Part 2 creates the self-organizing map that we see over here. It doesn't create the squares and the circles, just, you know, the different squares and their abstractions. And in part 3, we continue using the training data and we feed it to our now trained map, and we check where it places it. So it'll place it in one of these squares, and we calculate how many attacks and how many instances of normal traffic each square receives. And then for each square, we calculate a ratio of malicious traffic to total traffic. And this ratio is then used during the testing phase when we start using our testing data to evaluate the accuracy. So to evaluate it, we start putting in testing data points. The model will assign it to one of these squares, one of these classifications. We will check if that classification has an amount of malicious traffic greater than the threshold. And if it does, we classify the testing data point as malicious, otherwise benign. And then we check it against the true value of malicious or benign and sort it into true positive, true negative, or false negative to get our confusion matrix. So for this one, we got this confusion matrix right here. And this is about 31,000 data points that we used in our testing data. And they're all plotted up here as circles and squares, squares being benign, circles being malicious. But the main numbers we're concerned with are false positive at 257 and false negative at 647, which is reasonably good. In our other experiments, we were able to get much better numbers. So our best result came from setting the dimensions to 50 by 50, the threshold to the same, about 1/2, and we got 150 instead of 250, and about 300 instead of about 650. So there's a fair bit of improvement there. Basically, so far, the bigger numbers we use for the dimensions of our map, generally, the better the results become. Eventually, that should fail to be the case if you make it too big, but 50 by 50 took about 50 minutes to run. 20 by 20 also gives improved results at a much less expensive runtime. Overall, this being our best model, had about 1.4% of its classifications being incorrect. And this one, with the better runtime, had about 2.1% incorrect classifications, which are quite good. And this goes to show that self-organizing maps can be a valid option for detecting network attacks. Though they do, in order to evaluate the efficacy of the model, you will need to label your data, which is generally one of the advantages of unsupervised learning, that you kind of lose in order to evaluate it. I believe that's all we have for you today.